Welcome back. In this question, we're supposed to draw products, and they don't even tell us if it's SN1 or SN2 or what's going on. So remember that for SN2, you have inversion of configuration, and for SN1, you get both inversion and retention. So you need to draw both, okay? Stereoisomers that you get, and we sometimes say it's racemic, okay? Now, this molecule shown in part A, if we identify the leaving group, I've identified the alpha carbon. We want to now count carbons and determine if this is, primary or secondary or tertiary. Now, secondary alkyl halides can react by SN1 or SN2, so you have to look at other factors like the nucleophile. This is not a negatively charged nucleophile, so it's a poor nucleophile, and therefore it supports SN1, okay? So we can rule out SN2 as a possibility. SN1, we have to draw both stereoisomers. So remember again that alkyl halides react with water to give you alcohols, or alkyl halides react with alkyl halides react with alcohols to give you ethers, and alkyl halides react with water to give you alcohols. So here's our alkyl halide. It is chiral as a starting material, but when this reacts, you're going to form the product that has been retained, and you're going to form the product that's inverted. Okay, and you're going to form 50% of that, 50% of that, and we call that racemic. Okay, so we get the racemic mixture here. In part B, we again need to carefully decide what's happening here. Okay, so we identify the alpha carbon, and then we count how many carbons are attached to that. That's just one, so we call this a primary alkyl halide, and it occurs by SN2. So what's going to happen here is that this negatively charged nucleophile is going to attack, right? And normally it happens from the back side and kicks off the leaving group. Okay, kicks off the leaving group to give you the products. And remember that we want to show the inverted products. Okay, so if I do something like this, and I react this with the nitrile, I'm going to make sure I put wrong here so you don't just write this down and leave the video. If I write this, but I don't change anything, okay, all I've done is snap on this nucleophile in place of that, and I leave the wedge and dash exactly as is. That's wrong because it's still the same configuration. You can work through it all and everything, and you'll get the same for both. They're both R or they're both S. I can't do that in my head. So what you want to do is switch, okay? Take these two. If you switch any two groups, you will generate the enantiomer, and that's what we want to do. So switch these two, and what we'll do is we'll draw that over here. And, it's originally a hydrogen. Now we'll put a deuterium there. And originally that was a deuterium. We'll put a hydrogen. So hydrogen is just one proton and 0 electrons. And deuterium is one neutron and 1 proton. Okay, it's an isotope of hydrogen. I just am explaining that in case you don't know what deuterium is. So it's just like hydrogen, but it has one extra neutron in its nucleus, and so it has a different mass. So this is the correct product here that we want to draw. You need to flip a wedge and a dash. If the leaving group is on a wedge, let's say here, and I add, hydroxide ion to this, I want to, of course, flip the wedge to a dash. So I want that to be a wedge. Okay? So in this example, we had the leaving group was a line. So we have to do funky stuff to the wedges and dashes already in the molecule. But in this example, if you have the leaving group on a wedge, it's a little bit easier to operate with. It makes more sense. Okay? Anyways, I hope this problem helped you out, and thanks for watching.